Hello, Physics 135 students, and welcome back for another virtual class. I hope that you all had a nice week back from spring break so far and are eager to dive into things. S- Um, First, for our icebreaker, we'll be going into, I think, a pretty fun question. Do you think there are more grains of sand on Earth or atoms in interstellar space in the galaxy? So, just to be clear here, interstellar space would be kind of the regions between stars. So, it's not like there are going to be Earth like planets in that interstellar space. So, go ahead and pause the video and try to think of the answer to this question. Okay, so unpause. And I wanted you all to actually think about this independently before I talk through my own answer. So I'm just spitballing here, I should say. But in terms of atoms in interstellar space, there's roughly one atom per cubic centimeter. And then in terms of the size of the galaxy, uh, the Earth is about, or the sun, we could say, is about 8 kiloparsecs away from the center, and that's about two-thirds of the distance away from the center. Um, so, in other words, in terms of the galactic disk, that's about 12 kpc in radius. And if we think of the height, there's a thick disk that's about 1 kiloparsec. So, in other words, if we're thinking of a cylinder, we could do 2 pi r to, or maybe more appropriately, pi r squared times h. So again, our radius would be about 12 kiloparsecs, so that's about 144 kiloparsecs squared times 1 kiloparsec, so we have, and then times pi. So in other words, we'd have, well, let's just say roughly 400 kiloparsecs cubed. And then there are 3 by 10 to the 21 centimeters per kiloparsec. So cubing that, we would get 27 times 10 to the 63 centimeters cubed. So, in other words, 27 times 10 to the 63 multiplied by 400. Let's go ahead and say 27 is close enough to 25. So then 25 times 4 is, of course, 100. But we had an extra factor of 100, so we have 10 to the 4. And then we had 10 to the 63 otherwise. So then we're going to have a total of about 10 to the 67 um, atoms in the galaxy in interstellar space. So 10 to the 67 atoms in interstellar space. I kind of still think it's going to be more grains of sand on Earth, but 10 to the 67 is a pretty big number. So in terms of the Earth, let's just say that the entire Earth was made of sand, but that's a overestimate. So the Earth is about 6,000 kilometers in radius. And then if we were to work out the volume, that'd be 4/3 times pi times 6,000 kilometers cubed. Let me just go ahead and convert that one to meters first. So in other words, we'd have 4/3 pi 6 times 10 to the 6 meters cubed. So then we'd have 216 times 10 to the 18, 4/3 pi, the division by 3 and pi roughly cancel. So 216, I'll say is, let's just round down to 200, multiplied by 4. So we have about 800 times 10 to the 18. So in other words, we could say we have about 8 times 10 to the 20, and that's cubic meters. All right, and then in terms of sand, we'll just say that sand is like a rock, and the average density of rock is about 4,000 kilograms per meter cubed. So we have the meter cubed already, so let's figure out the mass. Admittedly, there's an easier way to get there. But so then assuming that density, we would have again, something like 8 times 10 to the 20 times 4,000. So we would get to about 8 times 10 to the 23. That's a little bit small. The Earth is about 6 times 10 to the 4, 24 kilograms. So I guess that's fine because, again, not all the Earth is sand. But in other words, the density is probably a little bit off. Okay. Or maybe I made a mental math error somewhere. That's totally possible as well. Okay. So we have 8 times 10 to the 23 kilograms. Now, how do I get that still into a number of particles? Um, uh, as far as sand goes, it's made of carbon and silicon. In other words, there are different elements. Now, the atomic mass of hydrogen is 1.67 times 10 to the minus 27 kilograms. And then for carbon, there's about 12 atomic units. For silicon, it's in the 20s. I want to say it's like 28 or so. So let me just work with carbon then. And so we had, again, 8 times 10 to the 23, and then we'll divide by 1.67 times 10 to the minus 27. So in other words, we're going to have roughly 10 times 10 to the, let's see, 10 to the 47. So in other words, about 10 to the 40s, 10 times 10 to the 47. So in other words, about 1 times 10 to the 48. And then we're only multiplying by about 10. So I was wrong. It seems like, at least by that estimate, there's only about 10 to the 49 grains of sand on the Earth. And actually, that should be a smaller number because I was doing this volumetrically. Whereas for sand, usually we think about like on beaches, versus atoms in the interstellar space, again, was like 10 to the 67. So anyway, kind of a fun back of the envelope calculation that's possible to do. A little bit of a longer icebreaker, admittedly. Moving on, really important. We're only about 2 weeks away. I guess it'll be a little bit less than 2 weeks away when this finally gets posted. For the semester-long research paper, you should have half your paper written by March 29th. A couple of you have started emailing me about your projects, which is great. If you haven't done so yet, you don't necessarily have to, but it would be good to check in with me. I kind of recommend it. Now, in terms of today, we're going to, kind of as promised last time, talk about different plasma processes, specifically recombination. Admittedly, actually, I don't have a lot of this. We will have the the name of this class appear the first 3 minutes, and we're talk about really the creation of elements and about the creation of the cosmic microwave background a little bit. Admittedly, these first and third items, I don't have as much material. We'll maybe do a little bit more next time. The other thing I'll mention is part of the reason why I felt like I could get away with the icebreaker, thinking through that a little bit more time, is that it's going to be a pretty short lecture today. On the other hand, I do have a lot of worksheets for y'all to hopefully enjoy and to really mm, become acquainted with the material at a more, we'll say, intimate level, or really dig a bit deeper than we otherwise would be able to get to just from, a lecture. And really, the first thing we're going to do is a warm-up worksheet. So these will all be on Brightspace. So this warm-up nucleosynthesis worksheet is really related to what you have been reading in the book so far, more so than what we've covered in lecture. So go ahead and work on this warm up. I'd expect this, I mean, it depends to some extent on how creative you are. I would think that this warm up should only take about 15 minutes. If you take longer, that's okay, of course. If you're quicker, that's also certainly reasonable. But go ahead and pause the video and work on the warm up worksheet first. Okay, unpause. So hopefully you completed the nucleosynthesis warm-up worksheet. Now, in terms of the lecture, we have these 8 goals for learning, although there will be quite a few additional attention checks sprinkled in. We have 3 of them, I think, in particular towards the very end, which are worksheets, as well as actually another worksheet on the earlier-ish side. So we have 5 different worksheets today. But in terms of the lecture goals for learning, we're going to talk about what are the 4 phases of matter. We'll talk about how a gas becomes a plasma. So that is, I guess, a plasma process. We'll talk about the 4 forces of nature and about the different eras of the universe, as well as the first phase of the universe, not to be confused with the different eras. We will discuss how the universe switched from being dominated by radiation to being dominated by matter, and then about when the domination by dark energy began, or we could call this the dark energy era, started. And then last, we will talk about how the universe cools as it expands down due to our particular process. And I guess I should say that these are really your attention check questions. There will be some additional things you'll be learning as well. Now, in terms of the 4 phases of matter, in terms of the familiar phases, we definitely see all around us solids, liquids, and gases. In terms of water on Earth, of course, for ice, very useful for playing hockey, a little bit less useful for walking across the road when it's very, very cold outside. For liquid water, very nice for surfing as well as swimming, lots of fun activities with liquid water. And then for gas, I can't do anything too athletic with it that I can think of. If you can think of something kind of fun, let me know though. And even though these are really all the same molecule, right? They're all water. So in other words, it's the same material. Nevertheless, the behavior of the material is very different due to changes in the chemical bonds, not, in terms of the dihydrogen and oxygen monoxide, but because of the way that those molecules interact with other molecules in terms of water. So in terms of that, again, the idea is that for a solid, there's this kind of like crystal lattice. So it's not just that it's water molecules, but the water molecules are kind of bound together in a very, tight structure, which is why it hurts to fall on ice. Whereas for a liquid, which happens when you melt ice, the liquid, there are some bonds, but there are a lot of molecules that are free to slide around. And so that's why we kind of slide through water, we can fall through water, be another way to put that. And for gas, really, there are no longer these bonds when we evaporate a liquid to form a gas. The idea is that every molecule is really kind of free floating or on its own. And then when we heat something up even further, we have dissociation, where instead of molecules, we have atoms. This is still considered a gas, by the way. And then after we get so hot that the atoms start to lose their neutrality, in other words, some of the electrons become free. This is what we would start to call a plasma now. And we can talk about this process starting at least for hydrogen at around 10,000 Kelvin or a little bit higher. And then at millions of Kelvin, eventually you get to a temperature where all the electrons are stripped from the nuclei, and then you really have a plasma. Usually the density is really, really low astrophysically, though. So you can even have collisionless plasmas, which could be considered a different phase per se than collisional plasmas. And there's a lot of active research in plasma physics, as we were talking about last time. Fusion is really related to these plasmas, so it's a very important area of research. Now, in terms of these phases, I mentioned that, okay, the density in astrophysical plasmas tends to be pretty low. Generally, there is a relationship between these phases and pressure. And for different substances, or different phases, I should say, there's a different relationship between the pressure and the other thermodynamic quantities like density and temperature. So on the Earth, we can have actually liquid water and water vapor coexisting at the same temperature, but by and large, that's due to there being different pressures. As you go higher in the atmosphere, the pressure decreases. As you get lower, 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 you feel the weight of everything above you until you end up with the liquid phase. And then the pressure gets stronger, stronger, stronger the deeper you get into the ocean. All right. And also in the universe, there are multiple phases that coexist. You learn a little bit more about that in Stars and Galaxies, although even more so in an upper level class. So, in terms of the phases of the universe, the idea is that in the beginning, or at the very start of the universe, we think that the universe must have been extremely hot and dense if we just kind of extrapolate backwards from today and think about um, basically contracting the gas such that the particles are closer, closer together, and therefore the temperature should be higher, higher, higher. Now notice that this plot stops not at 0, but at about 10 to the minus 43 seconds. That is what we refer to as the Planck era, and we don't know what happened before that, but we'll talk about that a little bit more later. So in terms of like the Planck era, again, we don't know what happened then. We need a theory of quantum gravity to understand this. But today, there are four known forces, and they're represented here. We see that there is the strong nuclear force, or strong force. There is the weak nuclear force, or weak force. There is the electromagnetic force, and there is the gravitational force. Or you can say gravity and electromagnetism are fine. And kind of interestingly, this happens as the temperature cools down, although admittedly gravity doesn't seem to have split more than once. So it's still kind of an interesting question. How much longer might we have to wait until there is a fifth force that appears? And who knows what might mark the transition of that fifth force, because all of these happened a very short time after the universe began when the temperature was still above 10 to the 15 Kelvin. So it could be rather cataclysmic, in fact. All right, so in terms of the Planck era, so this would be the times, at least quote unquote, before 10 to the minus 43 seconds. And really, we have no idea what would be going on at the Planck era. And we need, again, a theory of quantum gravity to understand that. So just kind of moving right along from the Planck era, let's get into the Grand Unified Theory era, or GUT era. For the Planck era, you could call this a theory of quantum gravity. You might also call this not a superforce, but a theory of everything. There was a very nice movie about Stephen Hawking's life, which, believe it or not, came out before he passed away. I was very surprised about that. Um, and anyway, so we have a potential theory of everything, and then we have a grand unified theory, is so-called grand unified because it would combine all the forces except for gravity. And we have some idea of what that might be in terms of combining the strong force and the electroweak force, although it is still an active area of research. And this ends after 10 to the minus 38 seconds, so still a very quick duration for that era. For electroweak era, this is so after the strong force has decoupled, but the electromagnetic and weak force are still, we think, um, part of the same force, really. There are a lot of symmetries, and there's a very well-developed theory for the electroweak force. So that's pretty well understood. And the idea is that this is the period of time in which elementary particles are appearing, whereas in the GUT era, the strong force hasn't split off yet, and therefore we can't really have like nuclei quite yet, or a lot of really interesting things. And this electroweak era is a quote unquote long era, at least logarithmically, in the sense that it lasts until 10 to the minus 10 seconds after the Big Bang. Then after the electroweak era, we have not just particles that were in creation, but we have annihilation between matter and antimatter. And for whatever reason, there must be some asymmetry, although we have not detected any experimental evidence for this quite yet, but there appears to have been a slight creation of extra protons compared to antiprotons. And this is very small. There's only 1/1 billionth extra proton, and then all these things annihilate. So we're just the remnants, really, of this earlier era. And so, in terms of this annihilation, the idea is that when an electron and an anti-electron um, collide, they form gamma rays. And when the energy is really, really high, similarly, we can create particles. These gamma rays come together and form electron and anti-electrons. When the energy is high enough, you can also form protons and antiprotons, and potentially even helium and anti-helium, although probably the energy was not really that high from when the gut era ended and the electroweak era began onwards. And so now, in terms of how this works, so for the gamma rays, they can form different particles, but it's related to their energy. So you can only form a particle when there is enough energy for that photon. All right, and next we have a worksheet. So I'd like for you all to, for your attention check 9, to work on the light matter and antimatter worksheet, or I've also called this particle creation, where you'll get to learn quite a bit more or think through like this process in a little bit more detail. So I hope that you all enjoy that. Go ahead and pause the video and try that worksheet out. It should be, I'd say, about a 30-minute worksheet, roughly speaking. Okay, so unpause. Hopefully you worked on that second worksheet. If it took you longer than 30 minutes, that's okay. If it took you less than 30 minutes, that's also not unreasonable. I will say that if you note, keep in mind that my estimated budget for this class is about 2.5 hours. So if you spend a lot more in terms of the lecture, which should be no more than an hour, but I think will be closer to 35 to 45-ish minutes. For the last few worksheets, if you don't have time to do all of them, then that's okay. Potentially, if a future class session is a little bit lighter, you can do some of those worksheets then. Okay, so for the era of nucleosynthesis, this happened after the particle era was done when we had, again, all that annihilation. We have now our electrons and protons. And then for the era of nucleosynthesis, this is when we might say the first few minutes began. This is technically all of this is within the first few minutes, right? But this is really the most crucial era. This is beginning at 10 to the minus 3 seconds, and when the cosmic hydrogen and fused to form helium, as well as trace amounts of lithium, admittedly, but really essentially nothing heavier than lithium. And the idea is that this lasted for until the universe cooled down to about 1 billion Kelvin. And that was at 3 to maybe 5 minutes after the beginning. So this class could have been called the first 5 minutes, but it's called the first 3 minutes with respect to Steven Weinberg book of the same name from the 1970s. All right. And then the idea is that after the universe cooled down, there wasn't really, again, like particles weren't able to get close enough together. The sun is not 1 billion Kelvin, but the sun is a lot denser, keep in mind, than the universe was at this epoch. Um, so there's that trade-off. So once the universe expanded and diluted and got low enough in temperature, then fusion stopped, we think. And then after the first few minutes, for a couple 100,000 years later, the idea is that the universe gradually cooled down, cooled down, cooled down. Once it dropped below 10 to the 4 Kelvin, or more specifically, due to the difference in abundance, roughly 3,000 Kelvin, and density, I should say, then we think that all the electrons recombined with the protons, um, and really this could be called combination because it's the first time it happened, but usually we call it recombination. Um, and so when you have neutral particles, the electrons are no longer scattering the photons, the universe becomes transparent to the photon energy, and therefore we're able to observe what's happened from the era of atoms onwards. And so this era of atoms really extends until we form stars and galaxies, which admittedly, we're finding some objects that are only a few 100 million years, some galaxies, in other words, only a few 100 million years after the Big Bang. So, as far as how long this era of atoms lasts, um, James Webb Space Telescope will continue to push that back, although there were some pretty good arguments from the conference I attended in Aspen why we really shouldn't expect to see galaxies beyond redshift of 14 or so. In other words, say 300 million years after the Big Bang. All right, and then again, this has actually been revised. So let me say 300 million years after the Big Bang, whereas we used to think it was around a billion years. Although there was some evidence from Hubble for older things, we just weren't very confident in it back then. All right, so in terms of this really fundamental shift in the universe that happened when the cosmic microwave background was released, this also marks the epoch when the universe shifted from being dominated in its radiation in its energy density by radiation to dominated by matter. In other words, the radiation wasn't uh, as effective, you could say, in terms of influencing the universe's state. The other reason for this is that as a relativistic gas is subject to expansion, it cools more rapidly. There's a eta minus 4 scale factor scaling for the radiation density compared to eta minus 3 for the matter density. And then the matter density, it does drop as the universe expands. And then if dark energy is constant, then just necessarily the matter becomes subdominant at some point. We think that that happened a few billion years ago. Actually, there is some evidence now that the dark energy density is not constant with time, but we're really in the infancy still of sorting that out. That was a big result about 1 year ago now. And as we get more data from the dark energy spectroscopic instrument and dark energy survey, we'll learn more about that. All right, so just like we were thinking about, okay, there were, there are four different forces. There could be a situation in the future where there rises a fifth force. Go ahead and just kind of wild idea. Suppose another era exists after the dark energy era. What do you think would mark that transition, and what would you call it? Just no wrong answers here. Go ahead and pause the video and think about this. All right, and so for myself, I would probably call this maybe the dark matter era. Maybe that's not correct because dark matter also drops off like the regular matter. Maybe this would be called really the big crunch era if the dark energy really weakens. Otherwise, I have no idea, but definitely fun to think about. Now, in terms of kind of moving on, so as the universe formed stars, those stars formed heavier elements. But then this is the abundance of elements that we see around us today, normalized by the abundance of hydrogen, which is the most abundant element in the universe, even if it's not the most abundant on Earth. And you can see that there is a big drop off from helium. So there's in terms of the numbers here, there's a big difference in hydrogen and helium, but then there's a staggering difference between helium and lithium, etc. And then there's still a low, like around 1,000 times more hydrogen than carbon, nitrogen, oxygen. But also it's kind of interesting, why is there so much more carbon and oxygen compared to nitrogen? Why are there all these bumps down and bumps up? So that is what you will be addressing, not right now, but this is another, we could say, goal for learning. to try to address in the future slides. So the idea is, and in terms of better understanding the abundance of the elements, let's think a little bit more about how the universe cooled down. So if the universe acts like a gas, and the universe is all that there is, physically speaking, then there cannot be an exchange of energy with the surrounding environment because, again, the universe is all that there is physically by definition. And in that case, the only process that the universe can undergo is a so-called adiabatic process. For other gas processes, you have to apply some transfer of energy with the surroundings. You can have like heating from the surroundings to the gas. You can have cooling. You can have uh, transfer of material in and out. There are a couple of different ways to do this. But so for an adiabatic process, when you have a gas expands, it ends up cooling. And the idea is that there's simply a larger interparticle separation, and you expect the particles, if they're colliding with each other, to collide less frequently, and therefore to um, basically it'd be like uh, if you're throwing an egg to each other, you don't slap the egg to catch it, you kind of gradually catch the egg. And so it's sort of the same thing. The particles would be losing energy as they make additional collisions as the expansion takes place. All right, so since the universe we observationally know is expanding, therefore it cools. So you've definitely read about that in the book. We haven't really covered Hubble's law quite yet. We'll be doing that in, I think, 2 lectures from now. Now, as the wavelength of these photons, as the universe expands, this also means that the photons stretch if it's cooling down. We have that just from the energy of the photons being, inversely related to the wavelength. So if the wavelengths are stretching, then the photons are less energetic. Temperature is a measure of energy, so temperature is going down. And in terms of, again, this era of nucleosynthesis, so this is happening as the universe is expanding, and cooling. Um, the idea is that the temperature starts at about 1 trillion Kelvin at 1 millisecond, and then this era ends again within the first 3 to 5 minutes when the universe has cooled to about 1 billion Kelvin. So at times much earlier than 1 second, the temperatures are high enough that we have a couple of different interactions or reactions. So you all might have learned about reactions in chemistry. These are more of atomic or nuclear reactions now. So we can have a nitrogen nucleon combined with a anti-electron, or what we also call a positron. So this has a net charge of +1. Therefore, this other side has to have a net charge also +1. So that takes the form of a proton, and then this other particle, which conserves uh, the what we call the lepton number, as well as the number of, so we have one particle and one antiparticle. So we have a net of 0. We could say total particles. We need to also have a net of 0 total particles in terms of matter and antimatter counting in opposite ways. So we have a proton, therefore we still need to have a antiparticle. This is a anti-electron neutrino. Now, it's kind of cheating per se because we think that neutrinos are their own antiparticle. I guess that hasn't been formally proven yet. That depends on whether neutrinos are Majorana particles or not. There's some other theories where that's potentially not the case. And then the other interaction that is happening is we have a neutron interacting with a regular electron neutrino, so not that anti-electron neutrino. In this case, we have 2 real particles, and then we need to end up with 2 real particles. And the 2 that we end up with are a proton, electron, so net charge of 0, still net charge of 0. And this happens while these interactions kind of back and forth are such that the neutron and proton ratio stays roughly 1 to 1. So in other words, we can have neutrons decay into protons, but we also have protons combined with electrons to boom, go back to being neutrons. And then as the universe cools, the problem, or really as the universe like ages, neutrons start decaying. Now their average half-life is around 7 minutes. I think that's actually a density dependent statement, but regardless, that's the half-life. And if there are, we said maybe like 10 to the 67 particles in interstellar space, if there are tons of neutrons, then you don't have to wait for half of them to decay. There will be some of them decaying much earlier than the half-life. And at around 8 times 10 to the 9 Kelvin, or in other words, around 8 billion Kelvin, this ratio has already dropped to 1/6. And in terms of that neutron decay, what happens is that, well, we start with the neutron, and then it spontaneously kind of breaks down and becomes a proton plus an electron. And keep in mind, this is one real particle, so we need to keep there being only one real particle. And we handle that by saying, okay, if there's a proton and electron, then we need an antiparticle, and we can keep overall neutrality in check if it's a anti-neutrino. In this case, it will be an anti-electron neutrino. We could also have interactions where we have muons in play, and then we would have muon neutrinos, and same with tauons. All right, so for the mean life of the neutron, I said it's about 7 minutes. Let's go ahead and go with this number of 880 seconds times e to the minus t over tau. Then after 3 minutes, we'll have the ratio of neutrons to protons being about 1 in 7, which we think is really important in terms of understanding the abundance of helium that we see around us today. So in terms of those first 3 minutes, the idea is that you simply have protons fuse with protons to form deuterium, and then you have deuterium nuclei combined to form, in this case, hydrogen 3. And then for hydrogen 3, these fuse with another deuterium particle to end up forming helium 4. So it's a little bit different than the proton-proton chain. Although admittedly, we still have like a whole bunch of protons, and ultimately the net result is you take 2 protons and 2 neutrons. But the total numbers are different. So we have 14 protons and 2 neutrons end up forming our helium particle along with 12 extra uh, hydrogen, or we could just say protons in the end. So overall, we still have 16 nucleons in both cases. And the result of this is that we expect from the Big Bang Theory that in terms of the, I should say by the mass, we expect 25% of the universe to become helium and 75% to become hydrogen then. And this prediction is in very good agreement with the observations that we've been able to make of the very high redshift universe. Okay, so for attention check number 12, this is a little bit of a thinker, I would say. Maybe it's going to be more obvious to you than it was when I was learning this a long, long time ago in a galaxy not so far away. So for the following abundance patterns, which do you think would be an unrealistic composition for a star? And again, this is by mass. All right, so go ahead and pause the video and give this a try. Okay, so unpause. So keep in mind that, again, from the Big Bang, we expect 75% hydrogen, 25% helium. Now, stars fuse hydrogen into helium. So we can have more than 25% helium, like 27% helium is okay, 28% helium is okay, 25% is okay very shortly after the Big Bang. It's only this case where somehow the star just formed mostly of hydrogen and not very much helium. That would be a head scratcher. This is unrealistic, or we don't think that this could really happen for choice B. All right. So in terms of back to this picture of the abundance of elements, now the reason why there are certain bumps up and bumps down is that in terms of helium, remember that there are four nucleons for the most stable form of helium at the very least. It turns out that in terms of just um, quantum mechanics kind of favors the stability of nuclei or nucleons, I should say, or nuclei that are composed of a number of nucleons divisible by four. So they're so-called magic numbers that are every two elements by, well, by the atomic number. So in other words, we have issues. We have big issues for lithium, which has five nucleons. Stable beryllium, I mentioned that usually it's kind of even, right? But beryllium is a little bit different. There is no stable beryllium 8. You need beryllium 9 to form. And that's a huge problem. And then also for boron, it's not that boron 10 is stable, it's boron 11. And therefore, because of those issues, you have far less abundance in lithium, beryllium, and boron compared to if you can get over that hump and just get straight from helium into carbon, like we were talking about last time in terms of stellar nucleosynthesis. So we're almost towards the end of the lecture. I'd like you all to work on the heavier elements worksheet now. So in terms of this heavier elements worksheet, the idea is that you'll be better understanding what I just talked through, but really in more of an investigative format, like why you expect, oops, this is a different worksheet. I think that I have it right here. You'll be better understanding why it is that we have like the abundance patterns. And for some of these questions, you will have to reference this slide or one of the other slides that have this image on it. Okay, so in terms of like the fact that carbon is so much higher in abundance and oxygen is higher in abundance, etc., this is evidence of a process that we call helium capture, where again you form elements by bumping up the atomic number by two, or the number of or the atomic mass by roughly four each time. And there are other processes. There's the R process and S process, which do allow for still creation of nitrogen and some of these other elements, but they're not as efficient, we think. All right, and so in terms of today, we've really talked about uh, how we end up with the amount of hydrogen and helium that the Big Bang made in the beginning. And then as we learned more about last time, it's really stars that make up essentially everything else, and in particular those kilonova are responsible for the heavier elements beyond iron. And now I'd like you all to work on attention check 14, the helium creation worksheet. And then after you're done with that, I'd like you all to work on, um, excuse me, it looks like I have my wires crossed a little bit here. So this should be ideally the carbon creation worksheet. All right, so heavier elements, and then uh, just go straight into carbon. So 15 total attention checks, and again, quite a few worksheets. So although this was a bit of a lighter lecture, still a lot of good stuff for you all to cover. I hope that you all enjoy the worksheets. If you have any questions about them, do feel free to send me an email, or of course, you can attend office hours. All right, take care, everyone. Bye bye.